Hello everyone. Today we are going to discuss the photoelectric effect. This is one of the most important topic in modern physics because the way we look at the wave nature of the light is completely changed after observing the results of the photoelectric effect. So I have divided this photoelectric effects into three parts. I will discuss this effect in three parts in three videos. Before going into details, myself, Dr. Arun Kumar, Professor of Physics in Department of Science and Humanities, MLR Institute of Technology. So before going into details, let us see the outline of the talk. First, I will discuss the introduction. It means what the persons observed the photoelectric effects and what are their assumptions and what are the theories they proposed during their observations. Okay. Then before going into much details of this effect, I will review the electromagnetic spectrum and the characteristics of the electromagnetic spectrum. After that, I will discuss the Planck's black body quantum theory of radiation. Okay. Then I will look at the how the light interact with the matter and what are the results we can observe from the light matter interaction. Then we will discuss the photoelectric effect. After that, we will look into the characteristics of the photoelectric effect. In the first video, in the part 1, I will cover the introduction and the review of the electromagnetic spectrum and the review of the Planck's quantum theory of radiation and the light matter interactions. In second part, I will discuss the phenomena of the photoelectric effect. In third part, I will discuss the characteristics of the photoelectric effect. Now we will see the introduction of the photoelectric effect. This first photoelectric effect was observed by the Heinrich Hertz in 1887 while he was validating the experimental observation of the Maxwell equations. So he observed that, but he could not focus on this one because he is very much interested in proving the experimental evidence for the Maxwell equations. But in 1902, his student Philip Leonard, he was trying to explain the photoelectric effect with the wave nature of the light, but he could not do it because whatever the result we obtained in the photoelectric effect does not agree with the classical theories. Then in 1905, Albert Einstein came up with the idea from the Planck's black body radiation. He took the idea of all the objects absorb the radiation only in terms of discrete packets or discrete energy levels. So means all the objects absorb the energy only in terms of packets. These packets we call it as a photons. Okay. Now we will see how this photoelectric effect is evolved and what are the theories were proposed and which theories satisfy the experimental results. Before going into details, let us look at the electromagnetic spectrum. So usually electromagnetic spectrum span of all the wavelengths including the 0.0001 nanometers to 100 meters. It means that it includes the gamma rays and X-rays, UV rays, infrared rays and radio waves. However, and we human beings are very much comfortable with the only visible light. It means that our eyes can detect the only 380 nanometer to 780 nanometers. In this 380 nanometer to 780 nanometers, there are 7 colors are there. One is the violet, indigo, blue, green, yellow, orange and red. There are 7 colors are there. And these colors, red color is having the highest wavelength and the less frequency, whereas violet is having the less wavelength, highest frequencies, means the frequency and wavelengths are inversely proportional. Red is having the more wavelength, less energy or less frequency, whereas frequency is having the less wavelength, high energy or high frequency. So if you look at this tabular form, here wavelength is tabulated, frequency and photon energies are tabulated against the different colors. For example, if you look at the violet, its wavelength is 380 nanometers to 480 nanometers, whereas red light, its wavelength is span from 620 nanometer to 750 nanometers. Means red wavelength is more, okay, and the violet wavelength is less. But when it comes to the frequency, wavelength is less, but the frequency is more for the violet. It ranges from 668 to 789, whereas for the red light, the frequency is less, 400 to 484, which is much less than this one. The red frequency is much less than the violet. Okay, similarly, photon energy of the violet light is 2.75 to 3.26 electron volts, whereas red wavelength photon energy is 1.65 to 2 electron volts. Means red is having the less energy, violet having the more energy. Red is having the less frequency, violet is having the more frequency. Red is having the more wavelength, long wavelength, and the violet is having the short wavelength. Means frequency or energy inversely proportional to the wavelength of the light. Okay. Now we will look at the Planck's quantum theory of black body radiation. According to the Planck's theorem, electromagnetic spectrum consists of wave packets. These wave packets or energy packets we call it as a quantas or photons. Means these quantas or photons carries the energy in terms of photons. Means energy of the photon is directly proportional to the frequency of the photon. Means if you remove this proportionality with the constant, that constant we call it as a Planck constant. The value of the Planck constant is 6.626 into 10 power minus 34 joules second. And there is a n is there, here n is the integer. Means it will represent the 1, 2, 3, 4. Means E is equal to 1 h nu, 2 h nu, E is equal to 1 h nu, 1 h nu, E is equal to 2 h nu, E is equal to 3 h nu, E is equal to 4 h nu, so on, so like this. Means all the objects absorb the radiation only in terms of wave packets or photons or quantas, and emit the energy only in terms of photons. Okay, here you can see, if you take one atomic system which consists of two energy levels, E1 and E2. We call it as E1 as the ground state, E2 as the excited state. So whenever you shine a light of photon energy h nu, then the electron which is in the ground state, it is excited to the E2 state. Okay, once it is go to the E2 state, it will stay only 10 power minus 8 seconds. After this 10 power minus 8 second, it is unstable. So immediately it will come back to the ground state. But while coming from since it is a E2 state is unstable state, immediately after 10 power minus 8 seconds, it will come back to the ground state. But while coming back to the ground state, it will emit the excess energy in the form of photon. That photon is having the energy which is equivalent to E2 minus E1. That you can see here. E2 minus E1 is nothing but the difference of the energy levels. That is nothing but the h nu. So all the objects in the nature absorb the radiation and emit the radiation only in terms of the frequency, only in terms of the photons. Okay. Now the energy of the photon is directly proportional to frequency, right? Now frequency of the photon is directly inversely proportional to the wavelength of the photon. So nu is inversely proportional to c by lambda. So where c is the velocity of the light, lambda is the wavelength of the light. So if you know the wavelength and frequency, we can also calculate the velocity of the light. Here you can see velocity of the light is equal to frequency of the light and the wavelength of the light. So if you know the frequency or wavelength, we can calculate the energy or velocities. We have seen according to the Planck's, what is the nature of the electromagnetic spectrum and what are the characteristics of the electromagnetic spectrum in the previous slides. Now we will see how when the suitable frequency of light falls on a metal surface, what happens. Now when suitable frequency of light falls on a metal surface, electrons are ejected from the surface. These ejected electrons are called photoelectrons, and the phenomena we call it as a photoelectric effect. Okay, usually here we are saying that suitable frequency. What do you mean by suitable frequency or suitable energy? So suitable frequency means the energy of the photon must be equal to the work function of the material. Usually in the material, so we have so many atoms, and in the outermost orbitals, there are electrons are there. These electrons freely detached from the atoms and they freely roam inside the entire volume of the material. Now, these free electrons, when they are moving here and there, whenever you shine a suitable frequency of light, those electrons, they can come out of the material and they constitute the photoelectrons and constitute the photocurrent. So basically, whenever you are shining the light, immediately the electrons which are roaming inside the entire volume of this sample, they come out of the material, means they are coming out of the work function, means because these electrons are held by the work function of this material. But when you shine a suitable frequency or suitable energy of a photon which is equivalent to the work function of this material, then only electrons will come out of that material. Otherwise, electrons will not come out of this material because that is held by the bounded by the work function of the material. Okay. Now here you can see in more details. So we are taking the potassium whose work function is 2 electron volts, and we are shining the different colors, and in other words different frequencies of light falling on a potassium surface. First case, we are taking the 700 nanometers wavelength or 700 nanometers of radiation, which has the frequency or energy which is equivalent to the 1.77 electrons. Here the photon energy 1.77 electron volts is much less than the work function of this material. So we cannot see the photoelectric effect with this material. Here you can see in the first point, what we are saying in the first point, if the frequency of the incident radiation is less than the work function of this material, no photoelectric effect is observed. Okay, no photoelectrons comes out of the material. Now in second case, what are we doing? We are shining the green light, and whose photon energy is 2.25 electron volts, which is little higher than the work function of this material. Now in the second case, you can see when the frequency of the incident photon energy is equivalent to the work function of the metal. So what happens? The photoelectric effect is observed, and the emitted electrons will have the zero kinetic energy. Here in this case, what is happening? We are shining a photon energy of 2.25 electron volts, but we need only 2 electrons we required. Only remaining 0.05 electron volts is converted into the kinetic energy of the material. Okay, to 0.25 is converted into the kinetic energy of the material. Now in third case, we are shining the blue light whose frequency or energy is 3.1 electron volts, which is much higher than the work function of this material. Okay, here you can say in third case, when the frequency of the incident photons energy or frequency much higher than the work function, then what happens? Electrons are ejected from, means photoelectric effect is observed with and the ejected electrons will have the maximum kinetic energy. Here you can see 3.1 electrons minus 2.0 means 1.1 electron volts is converted. Out of 3.1 electron volts, 2 electrons are utilized to remove the electron from the metal surface, and remaining 1.1 electron is utilized for the kinetic energy of the material. Okay, so this is now work function. Okay, if you look, we are talking about the work function is playing the crucial role in ejecting to observe the photoelectric effect, right? So what is the work function? It is the minimum amount of energy required to remove the electrons from the metal surface to infinite. Okay, what kind of photon we are shining? We are shining a photon with the energy which is equivalent to the work function of this material. Okay, so basically what is the photon? Photon is nothing but a h nu. Nu is nothing but a what? C by lambda th, lambda by c, because frequency is inversely proportional to the wavelength. So this is the suitable frequency, we can call it as or we can call it as a threshold frequency, or we can call it as a minimum frequency. This is the minimum frequency required to observe the photoelectric effect, because this minimum frequency is sufficient, is equal to the work function of the material. Or in other words, instead of saying it in frequencies, we are saying it as a wavelength. This is the maximum wavelength. This is the maximum wavelength or threshold wavelength is required to observe the photoelectric effect. Here we can see some of the materials are there, their work functions. So we can see aluminum is there, copper is there, okay, zinc is there, silver is there, okay, lead is there. So different materials are having the different kind of work functions. Okay, so whenever you shine a light of suitable or the energy which is equivalent to the work function of that material, then only we can see the photoelectric effect. Okay, so as of now we have discussed the review of the electromagnetic spectrum, and we also reviewed the Planck's black body radiation, and after that we discussed the light matter interactions. In the coming, this is all for today. In the coming sessions we will see the other effects of the photoelectric effects and the Einstein's Planck quantum theory of photoelectric effect, and we will see in the next slides characteristics of the photoelectric effect. Thank you.